All right. So this PowerPoint then. So this is going to be a kind of general overview of C++, starting from pretty common basics that you already should know, things like classes, templates, references, stuff like that. And then move on to the standard library and some cool stuff there that I just want to quick highlight. And then moving on to more advanced C++. Nothing here is going to be too crazy. Smart pointers can get a little complex, but like it's nothing here is going to be esoteric. I think everything in this PowerPoint is something I use on the daily working with C++. But it should hopefully highlight some more stuff to look into. It'll be, I try and go over things reasonably well, but there's always going to be more to dive into. This is going to be more of a survey of C++ essentially, from like a modern perspective, which is good because I don't think there's many resources like this. Please go to the next slide. There we go. All right, so in general, I guess everyone should know this, but C++ is about the most general of programming languages ever. You can do pretty much anything in this, and that's kind of by design. That's kind of what it's designed to be, is that you can basically program it however you want. So you can program it like C, you can program it as like Java, basically, like purely object-oriented. There's functional features, actually. So you can really kind of treat it as whatever programming language you want. Generally, it's taught as C with objects, which is kind of where we'll start at. But really, there's a lot of these extra features I'm going to talk about are from these other areas, like functional programming, for example, that are outside of just C with objects that I think is normally taught. Probably one of the most. Oh, wait. Next slide. Generally, the idea of C++ is really to increase abstraction over C. Like, that's the fundamental goal. And so pretty much everything in this, especially in the standard library, is going to be towards the end of abstracting over something in C that was unsafe or annoying to do. That'll become a lot more obvious when we get to like the standard library. But also increasing safety. Like I mentioned earlier, a lot of stuff we'll go over that you probably haven't seen, like smart pointers, RAI, is designed to increase safety, avoid seg faults, that sort of deal, that C is, of course, notoriously quite prone to. And then as well, because of all these features, all of this is going towards the ability to write a lot more general, powerful libraries, so things like Rust, things like OpenCV. The reason you don't see these as much in C, although they have C APIs, is because C++ has the level of abstraction that makes these much more feasible to use. And that's really the driving motivator behind C++. And then as well, its standard library is way better than C. Oh no, not the whole lecture. So this down here, this is a talk from the creator of C++ at C++ 20's release. So that was the 40th birthday of C++, which is insane to me. I'd highly recommend checking out this video sometime if you're gonna, if you want to use it long term. I'd highly recommend checking out this video because he goes over basically what I just described, but in like his perspective. And what I love so much about like the guidance of C++ is that they all want it to be better. And so a lot of the features I'll show today are kind of that, making it more closer to like something like that Python rather than like as arcane as at least I think of C++. And so I think it's a really cool perspective because it shows the, like what his vision is for how you should use the language, and it's a lot more forward-looking than I was expecting. Anyways, it's a very good talk. So very important for C++ versus most languages. It's an ISO standard. So that means it's designed by a committee. They have this is C++, but they don't implement it. So basically they draft a standard, but not an implementation. And it's up to your Microsofts, your GNUs, your whoever makes Clang, Apple, I think, to actually implement this C++ standard. And it leads to a few things, like you have alternative standards. So basically each version of the language, what would be like a Python 3 or 2, is the year it's released. So if I say C++ 98, that's the ISO C++ standard from 1998. And recently it's every, 3 years, I think? Yeah, every 3 years they do an alternating major release, minor release. So like, this all started in 2011. With a huge revitalization of the language. Like you should be using at minimum C++ 11. This was like a huge port over from 98. 98 was really getting stale. And C++ 11 aimed to like make it a modern language, really. And so that's like what our CIS 200 here is based off 11, the textbook, if you actually read it. They don't really teach it that much, though. Um, 14 was a minor bug fix. 17 added a ton of quality of life features, which is why I really like it. And it's still really standard. So like in my experience in industry, this is pretty much adopted. Mine is like embedded, which is forced to use like ancient stuff. But mostly C++ 17 can be considered like modern C++. Like this is expected. And then C++ 20 and 23 are also huge. Like they're complete shit. Like they removed headers, or not removed headers, but they replaced headers with like actual packages. And stuff, so you can have like actual package managers now, and there's like a bunch of cool concurrency features. Like it's almost a different language. It's crazy, but it's taking forever to be caught on. Even tools are barely there yet. So, and stuff like Rust doesn't support it. So it's gonna be a long time, I think, until we can really use it. But it is a nice thing to look forward to in the future. Like, you know, obviously, C++ will be around for a minute, so you're going to run into it again at some point, and it's good that it's still, you know, trying to improve.
When you install C++, will it tell you which version you install?
It's a good question. So it depends on the compiler you have. This is the problem. Is it's not like I am using, again, Python 3.2. It's I have a compiler, and that compiler is compatible with some of the standard. So there's a document on a website I'll show later that shows which features are implemented by which compilers. So like C++ 20 is a perfect example. Some compilers implement most of C++ 20 minus like 3 huge things. And so depending on the compiler you're using will change what parts of the language you can use. So generally in like something like ROS, using CMake as its build system, you can specify which version you want. And that's generally a sane thing to do. But yeah, it's pretty messy. Generally, I, and well, seemingly industry, likes to stay at the version that's generally fully implemented, which is 17. Maybe 20, I haven't looked at 20 in a minute, but right now C++ 17 is like every compiler has it fully implemented, so you won't get surprises. But yeah, it's purely up to the compiler version is the only factor. All right, so first off, I'm just going to go through some fundamentals. I won't dwell too much on these because this is actually what I teach, but seeing as not everyone is even that far, it's good to at least mention these. So obviously classes are the core of C++. It is literally the reason it was made, because it was originally C with classes. These are classes in the object-oriented sense. So basically, it's a abstract data type where data is alongside actions to be operated on that data. That's like the most fundamental area of classes. So in C++, in C++ terms, I think it's member variables and member functions. I'll call them fields and methods because that's what Java does, and that's just kind of what people say nowadays. But you'll hear those interchangeably. But basically, that's it. That at its core, that's all objects are, is essentially structures and operations to act on those structures. And so the cool thing is that in C++, because it's a native programming language, it is literally C structures with methods. And it's just it's entirely a syntactic sugar for having a struct and calling a method on the struct. And I'll show in a second what that looks like to compare. But this is actually like relevant for ROS and stuff, because using function pointers, you'll have to interact with this. So here's an example of C versus C++. So here's a struct in C, and just a function that will basically take a pointer to an uninitialized version of that struct, take its parameters, and fill the struct with the parameters. So this is a bit, useless of a function, but still it'll be useful because that's literally identical to the equivalent C++ constructor. So you can see the actual syntax is pretty much the same. In C++, class and struct are almost identical, so you can swap the terms and it still works. It just changes like access modifiers. But you can see the syntax for them are the same, and in terms of like the C style, the order of fields you declare is the memory like address of those fields. That's true. So if you have cost and then 2 char arrays, in memory it will be that int and then 2 char arrays. So you can use it to interact with C like that. The key thing though is that this function here is the automatically generated constructor. So you can see like the equivalent use. If you're in C, you do something like you default create your uninitialized structure. You then pass a pointer to it and pass your variables. The equivalent in C++ is just calling the constructor. So this is all just to point out what the point of like constructors and what these methods are. Fundamentally, all it's doing is creating syntactic sugar around creating a struct on the stack and then passing a pointer to that to some function. All it's doing is in C++, it's just hiding this first struct. So I think yeah, here it is. So you can see it a bit more directly here, but like this is the equivalent between the two. So you have a, did I define car price? Yeah, here it is. It's like this car price here takes a pointer to some struct and then does some operation with the struct's members. A C++ class function is a literal one-to-one abstraction over that. So under the hood, having a function like this that takes a pointer, and you would call it, you know, by passing a pointer to the function, or using the dot operator to access it, these are literally the exact same under the hood. The only difference is that C++ hides the pointer from you. But otherwise, it is literally the exact same. I don't actually have an example of this, but this is relevant in ROS, because if you have a subscriber, and you have to bind a function, or you have to, you know, have a function pointer to a callback, that callback, that function pointer, will have that first pointer that's normally hidden from you, which is why you need to do, you'll see in like my template, I have stood bind, which I think we touch on later, the function pointer this, and then it binds that this to it. So all that's doing is it's calling that function pointer with the this pointer. So you're literally doing the C version again, because under the hood, C++ is the same. So that's the only reason I mentioned this, because this confused me for forever. But you know, under the hood, if you're dealing with the raw memory, you will be touching it like it's C. What's actually on here? What I already said. All right, so access. Pretty basic, but C++ has Java-esque private, public, protected members. I know you're well aware of this now. We don't really touch protected much. Protected just allows subclasses to view it. I don't even really touch on inheritance much here, because it's honestly not that great in C++. Like, you can do it, but it's not like it's not as guaranteed as it is in other languages. But still, these are very useful. I highly recommend using private to encapsulate. Essentially, the idea here is you only expose what you want people to be able to see. So like, the idea is that for anything you put in the private section are implementation details that you want to be able to change however you want, and it won't affect people's code. So for example, let's say you have a heap structure, right? And there's like a get function for like get top or whatever, and a sort method. In this case, you would put that backing like a raw array for that as a private variable. The idea being that, like in C, you could just access that raw array and just completely screw with it and just completely invalidate the heap. But in C++, it is impossible to access that raw array, whether purposely or accidentally, and that basically allows you to know that I know no one's tampered with my data, and so you can treat like things like the heap invariant as actual invariants. If you've heard of encapsulation before, this is what encapsulation means. It's hiding your internal state. This is something that is taught a lot and people like understand and can quote back, but this is like actually like 90% of clean code and like code reviews I do is people not doing this, of like having like
Properties of public and private.
Yeah, it's like making encapsulating data into classes and then making things private. Or because it'll either be like 18 variables in a function, and I'm like, please put this in a struct, or they'll have a class that everything is public in. And there's like 50 helper functions that are just divisible. Like, just moving those, making those private, keep minimizing the API of your method or class to only things people would actually need, just makes code a lot cleaner and just easier to work with.
If my understanding, the difference between class and struct is class is default, it's private, and the struct is default.
Yeah, that's a good point to mention. If you do a struct, everything is default public. If you do a class, everything is default private.
That's the only difference.
That's literally the only difference. Yeah, that's only for C compatibility, because in C everything is public because there's no private. So if you do a struct in C++, it's the exact same as C, because they want you to be able to copy paste C code into C++. Generally, I use this as structs are raw data that, like, it's basically like I want everything to be public, like a vector of like XYZ. But if a class is for more like advanced stuff, like, you know, like a web request or something. All right, here we go. So I don't remember how much they teach this, but constructors in C++ are really hard, and I don't know why. So really, unlike other languages like Java or Python, there's actually 5 different kinds of constructors, and this is actually extremely relevant because a lot of APIs really depend on this, especially ROS. This is actually pretty important to understand. Also fun, they're all called implicitly. So just depending on the context you call them, it changes which one's called. So I'll go over here and then I can show like what they actually look like. Default constructor is called when nothing is passed. So if you just do like your class and then you just declare a variable with a semicolon, it will call the default constructor. Or if you use the empty brackets constructor, that's also the default constructor. Normal constructor is any other constructor than the other ones I'm going to mention here. This is what you'd expect. You probably understand. Copy constructor is when you have a constructor that takes an instance of the same class, and exactly one. And in this case, that will be called separately to copy the struct. This also occurs if you do, I believe if you don't override equals and you have a new variable equals an old variable of the same type, it will call a copy constructor through the equals operator, which is it's stuff like that. Like that's why it's useful to understand these, because if it's a different copy constructor that does different things, you have to know that that's what's being called. Move constructor. This is one I can guarantee you haven't heard of. Basically, move constructors are called whenever it's an instance of the same class being passed as an argument, and that class is about to reach the end of its lifetime, which is a little weird. So basically, think you're returning from a function, and you haven't bound that return variable to a variable yet. So like, for instance, if you call like add 1 and 2, and it returns an int, right? If you have just call that without assigning that int to anything, it gets assigned to the stack, and then immediately you never use it. So its lifetime ends. Its lifetime being essentially its scope, more or less. So what the move constructor does is, let's say you have a linked list, right? That's like on the heap, and you're assigning that to another linked list. And that first linked list is like returned from a method. It's about to go out of scope. Logically, there's no reason to copy all of its data to the second one, because you're going to copy it all over, and the first one's just going to be destroyed anyways. So what the move constructor allows you to do is to take the resources from that first list that you know is about to die anyway, so you don't care what state it's in, and move it to the other. So like the linked list example, the move constructor would like take the head pointer and just copy that head pointer, which is more efficient than copying the whole thing. So the way this is actually used, I'll touch on this way later, but this is used to pass resources. It's like if you want to make sure there's only ever one, like either like if you copy an object and you want to do a full copy, you want to copy like a backing file. But if you move, you just pass the handle to that file. So this, again, we'll touch on this later, but that's an important one to understand because it's a lot more tricky. And the destructor is just a function that's called when the struct reaches the end of its lifetime. We'll also touch on this later. Here's what they actually look like. Default is, like I mentioned, it's just empty. Normal constructors are just, they take variables. This one's easy. Copy is a const reference to the same class. It has to be specifically a const reference for some reason. And then this will be your copy constructor. And then move is the same, but with 2 ampersands, which stands for a moved variable. Don't worry, I don't really touch on move too much because it's like honestly not really that useful for 90% of your work. But just know if you see 2 ampersands, that means a value that's about to die, called in R value. But it's almost like compiler internal stuff. Destructors are just a tilde in front of a constructor. It's super easy. And then these are how they're called. If you notice, they all look exactly the same, which is why it's useful to understand what they all are, so you know, oh, I'm passing the same instance, it's going to call a copy constructor. And also here's the instance of that move constructor I was just mentioning. So you'll see we construct a car that immediately dies. So we put the car that immediately dies into the structure that we're constructing, and then that will call the move constructor. So again, just an example of that. Don't worry too much about moves.
Whenever you declare an object or like a variable or something like that, you're going to initialize it through a constructor. Is that how it works?
Yes. In C++, you have, well, yeah, at some level you have to use a constructor. Yeah. There's no other way to do it, because you can't, unlike in C, you can't. Like in C, you can just declare a struct on the stack, and that's just uninitialized memory that will segfault if you access it. In C++, if you try to do that, it will call the default constructor.
That's the case in Java too, right?
Yes, yeah.
C?
Or no, it's like C++. In Java, you also have to call a constructor. You can have a static method on a class that returns an instance of the class, but under the hood, you just have a private constructor. So at some level, you must use a constructor. Although I should mention, if the default constructor of a trivial object, so it's like a C struct, is literally identical to just doing it in C. So, or actually, no, I'm wrong. Actually, this is important to mention. So if you default construct a primitive type, so that's a type from C, So like ints, floats, arrays, a struct made up of only those, it will actually be uninitialized memory. So I was actually wrong. So if, for instance, you have a struct of XYZ ints, and you just do a semicolon without a constructor, that will be uninitialized memory that will segfault. So in that case, you have to manually call the empty constructor, and then it will initialize all those variables, and it won't segfault. So that's actually a very important thing. Generally, what I do is I always explicitly call a constructor, just to avoid that empty uninitialized memory. Because like we're not on microcontrollers, we really, well, most of us, anyways. So we really don't care about the extra 1 kilobyte of ROM used or whatever. All right. So there's a lot more to classes. I'm not touching these. This is mostly inheritance and polymorphism and stuff that, in my experience, you really don't use much in C++. It's really actually kind of hard and complicated compared to like Java. Also, the concepts themselves are like very not a now problem. But just be aware you can do all these things, and operator overloading in particular is cool. You can overload plus or minus or equals to change what they do. Just something to be aware of. But yeah, these are things I would just look up as you encounter them, really. All right, I guess, do you have any questions on classes? No? Cool. Okay, time to stuff that I don't know. I didn't discover these for a while, so I don't know if you'll know or not know these. References. References have been in C++ since the beginning, and they're super cool. Basically, they are literally just a pointer, but that pointer can never be null, and you can never reassign the pointer. This is another thing that is subtle, but like people need to use them more. So if you see on the right, you can see like we're taking this car by a reference and then by a pointer. And you can see it's under the hood, it's just a pointer. Either way, it's still passed by reference semantics. But in the one with reference, we use dot instead of arrow because we're not like actively dereferencing it. And then the other thing is that we can't reassign the pointers. So like in this car example, we can just assign this pointer to literally wherever, and there's nothing the person who's passing that object in can do about that. So you just have to kind of trust that that function doesn't just destroy your pointer, which is quite silly. And in this case, that's just a compile time error. Likewise, it's completely legal to pass a null pointer in here, and this would segfault. And you have to, for every single function, defensively check if someone passed a null pointer in, which is just really annoying. With a reference, that's a compile time error, which is super nice. So really, in my opinion, you should never use raw pointers in C++ unless you're on embedded and you're like, I have a peripheral at x51502, and like, you need to actually like point to a memory address. For all intents and purposes, the reference type is just the correct one to use. And I guess to be explicit, it's always type and then ampersand. Const. So const is another one that's been around for forever. It simply makes the type immutable. This is really powerful in C++. This is actually way stronger than const in other languages. I think JavaScript also has const, which actually JavaScript's const is pretty close. But basically, you can put const pretty much anywhere in front of a variable or in front of a type. And then that means that you can't, there's two things. One, you can't explicitly overwrite that type. And two, if that's a class that's being const, you can only call methods marked const. So I believe I do actually show that. Here it is. It's like on the right here. This is what it means to declare a method const. So you have our normal method signature, and then at the end, before the body, you put the word const. What the const method means is you're not allowed to mutate fields of your class. So basically, this is basically and if you do, it's a compile time error. So basically, the reason it does this is if you declare, like we have our const car reference here, which is just an immutable reference, you can see we can't overwrite the cost here. The reason you have to mark methods const is the compiler trusts that you don't mutate that class, so it's still constant. And that's the kind of the purpose there. So const is super, super useful, especially with references. I'd almost always recommend adding const unless you don't need it, because that way if you accidentally mutate something, it's a compile time error. So it's just kind of a don't accidentally overwrite things, or like if you're writing a function that takes, like for instance, I just wrote one for our computer vision stuff that takes an image, and it's pretty common in like OpenCV to overwrite parts of images in an algorithm, but it's also useful to know I can keep using this image after to avoid a copy. So in my case, I do const references to that CV mat, And that means that to the people calling my function, they know I literally cannot edit their value, so they don't have to copy in the future. They can trust it's the same as they passed in. So like that's kind of the value of const. Templates. Have you guys reached templates in 200? The 200 guys? Yes? Actually, I remember you were working on this like yesterday. So templates are actually extremely complicated. So they're C++'s generics. If you use Java generics, it's the same concept. The thing is with C++ templates, they're a lot more interesting. So basically, the template's actually a good word for it. It is literally a function that at compile time will be copied for every single version. So for instance, you have this template here with 2 types. For each call, which you call like this with type, comma, type, for each version of this function you call, so int float, 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 float double, it will literally compile a new version of that function. So you're templating those versions. That's where the word template comes from. And how it's templated is defined by its normal method body. So this is pretty self-explanatory. Like if you use a type name t and you use t here, that will be filled in by the type that you replace it with. Pretty simple. The interesting thing with C++, though, is that you don't restrict that. Like in Java, for example, you say it has to be a subclass of X. In C++, it's duck typed. So basically, how you use the type in this function will determine if you can use that type as a template replacement. So like, for example, in this function here, we have type name t. T has to have a default constructor because we call a default constructor. T also has to have a variable we can access with .x, and O, which is the other one, must have a method fly. So these are all like defining an implicit like structure that these templated variables have to follow, or else it'll be a compile time error. And so if you ever see C++ spew out like 80 million years of errors because it's like cannot find the right version of the template, and it goes through like every single version of the template, that's because whatever you passed in here didn't meet one of these like implicit contracts. So this is a little like complex and annoying. But the nice thing is that means you can do ridiculously generic stuff. Like for example, I did like a little ray tracing thing in the past, and I wanted to use both vectors from ROS and OpenCV, and both of those are just structs that have .x, .y, .z. I think I said vectors, yeah. And so what I did is just a function that calls just that generic type and then .x, .y, and .z. And because those are both valid options, those both compile, I was able to combine 2 separate libraries into the same API. And so that's the kind of the benefit of having it like this. The downside is that the errors are awful. I'd say in general, avoid doing these unless you absolutely have to. This is more useful to understand as a user rather than a provider. Because they're very hard to get right. Google bans these at work. that's the level of difficulty with templates. So they're one of those things that's like only use if you have to, or if you're writing a library, basically. But nonetheless, again, it's useful to understand. Namespaces. Now we're getting to easier stuff now. Namespaces are simple. They literally just add a prefix to your class. This is another thing that I feel like people should know, but a lot of people don't. So you declare them just by namespace, and then you declare a scope. Anything in that scope is in that namespace. And so if you've ever seen like namespace std or std, whatever you want to call it, for a standard library, that's also namespace. So if you've seen that : operator for that, that's just in that namespace, I want this struct. The entire purpose of this is, one, to just make it easier to find stuff with autocomplete, in my opinion. But then from a technical level, it's so you can have 2 classes of the same name. And you'll put one in one namespace, one in the other, and you can discriminate between 2. Okay, cool. But if you think about this real quick, this becomes extremely obvious, and this is one of the biggest problems with C, in my opinion. Because let's say I have a function absolute value, abs. I have OpenCV, the standard library, and an RTOS. All 3 define abs. That's an instant compiler error. In C, that's why you have in C, if you ever use C, it's like OpenCV _ abs for like every function. That's because they're just manually namespacing in function names. In C++, we don't have to do that. This is just good hygiene. I try to pretty much always put stuff in namespaces, just because you'll never know when someone else's code has the same name. And it just makes things easier in the long run. Now, you can do the evil using namespace. So using namespace is basically it takes that namespace and essentially puts this entire file in the scope of that namespace. So in the scope using namespace is in, so this could be in a file, this could be in a function or a class. In that, you no longer have to prefix. So if you do like using namespace std, which is an absolute classic in entry-level CS classes, you no longer have to do like std cout. You just do cout. I really, 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 really do not recommend doing this, because if you run into that case of you're using OpenCV and the standard library, now you start getting into like arcane linker errors if they both have the same symbol name, like absolute value, for example. But using namespace is still useful in a function. It's like in a specific function, if you want to like not have to type out CV or whatever, you can use using namespace CV in that function, and then that for that function you just don't have to type it out. So that's more of when I would use it. It is still very useful because some namespaces are huge. But yeah. Oh, it's particularly the standard library, because the standard library is huge, and
Yeah, fair.
like remember, it defines the symbol E, like the letter E. So if you're using namespace std, you can no longer use E for a variable name because it'll shadow the standard library. And there's like it's huge. The standard library is just so massive. You don't want that all in global scope, because and the problem is that the way the linker works, which I'm not going to get into, makes it so it's super common to have really weird compile errors that don't make it obvious that that's your issue, that you have two colliding symbols. So yeah, that's just, again, good hygiene. All right, now to actually useful stuff and, you know, probably a lot faster as well. Standard library, the STL, the standard template library. So this is C++'s standard library. What I'm going over is not all of it. It's huge. It's like hilariously huge. I'll show a document at the end that you can look into. Like there's calendar libraries, there's time libraries, there's concurrency, there's structures, there's like, there's not networking annoyingly, but there's a lot of stuff basically. And so I'm going to give kind of a greatest hits of the STL. These are a lot of these are things that like I see people using the C equivalent of, and I'm like, just please use the STL version. They're all almost unequivocally better because they're almost all zero cost. So string, this is the one you've probably used. It's a string. This is actually something that, again, if you're coming from C, it is really useful to know this exists, because in C, there is no string. You just use char stars everywhere, you know, a const char array for all these, or just a char array for them. This is literally just a heap allocated array, and it manages the size of the heap for you. So if you're ever using strings in C++, just use this. Like, it's just literally better in every way. And if you need the C string back, there's a function called .c_stir that will give you the raw C string to pass to like printf or something. Again, pretty basic. You've probably used this before, but please don't use char star arrays. It kills me whenever I see it. The only time you should use that is if it's something that's only ever going to be compiled into the executable, like the name of a window, for example, just because then it's not on the heap. Vector, another classic one. It's just an expandable array. I assume everyone here has worked with vector before. Cool. Pretty basic, but again, pretty useful. Array. This is the one I don't see people using, and it annoys me a lot. So this is literally a C array, but better. There's literally zero reason to use a C array in C++, in my opinion, because std array exists. So basically what it is this is just a zero cost wrapper. So it adds compile time, but it adds zero runtime cost over using a raw, like, you know, int array of 5 or whatever. So basically the way it works is via templates. You have your type, and this is your size of your array. And then it works exactly the same. It's like these two statements are exactly equivalent. The only difference is that this provides like methods that actually give like things like the size of the array. You no longer have to have a hash defined for the length of every array. You can do things like it has access to iterators. It has like a, you know, does it contain this variable? Like a ton of these quality of life features over normal C arrays. And so a lot of people I see just use std vectors for this. But then that's on the heap for no reason. If you still want it to be on the stack, still want it to be really efficient, just use std array. Again, it's pretty much directly superior in every way. And I forget if there's a function like this, but you can definitely pass it as a C array. I think it's called .data. There's a function called .data or a member called .data that will return the original C pointer. And then you can use it like a normal C array if you need to. This is a huge one. I would really recommend doing this. Also, unlike a C array, if you pass this by value, it will copy. Because C arrays under the hood are just pointers. So when you pass it to a function, that's passing by reference. with the std array, if you pass an array by value, it will literally copy the entire array. So you have to use references instead. Just be aware, because that's something that if you're passing like a massive array for like an image, copying that instead of passing it by reference is like a very significant performance decrease. Hash map. This is a dictionary map, whatever you want to call it. It's that. It's pretty easy. If you use Python, you're good friends with this. Just another thing that's just nice to have in the standard library. I would use unordered map and not map. This is a common flaw, is that map is ordered, so it's a binary tree, whereas this is you implemented in 350. I forgot what it's called. Anyways, it uses a vector as its backend. Point being, an unordered map has constant time lookup. A ordered map has n or n log n or n log n lookup. So it's like a pretty significant performance difference. So unless you need ordering, use unordered map is basically my suggestion. So this is a dictionary or map, whatever you want to call it. So key value pairs. This defines the key. This defines the value. This insert or assign means if basically regardless of if the key 1 exists, if it doesn't exist, create a key called 1 with a value of the integer 1. Or if 1 already exists, overwrite its value with 1. And then the way you get that is by this index operator. So this retrieves the value associated with the key passed. So in this case, our key is 1, and it returns 1 because we inserted up here. Yeah, and the cool thing about the structure, I guess if you haven't had 350 yet, is that it is constant time lookup. So unlike, for example, you could store an array with all of these as like tuples or something, and then every time you have to use a search algorithm to find where it is in the array. That's going to be n log n, I think, at max speed. And this is constant time.
If dictionary was 1, then it would return the ONE then?
No, it's one way. It's one way.
Oh, it's one way.
So under the hood, it uses under the hood it uses hashing, which I'm not going to get into how that works, but it uses hashing to. That's why it's constant time. It's a function that converts an object into an integer, and then using that, whenever you pass in this 1, it gets converted to an integer and then just does like a lookup. And so that's also why it's unordered, because there's no natural ordering to a bunch of hashes. Tuples. So I just mentioned tuples. If you used Python, you're good friends with these as well. This is another thing I feel like most people don't realize is in C++, but it is since 11 or 17, one of the two. Basically, this is if you find yourself creating a struct called toInts and a char, just use a tuple. Basically, it's just defining a structure of these template parameters, and you can have infinitely many. I believe, yeah, I'm pretty sure you can have infinitely many. So you can have like 52 ints, and you don't want to have a struct with 52 ints. Just create a tuple with 52 int template parameters, and it will do as you ask. So use these for like data that you don't really want to create a struct for the one time you use it, but you still want to not, like for instance, returning from a function is the big one, because obviously you can only have one return type. So instead of creating a struct just for this one use case, just make a tuple. So like a good example would be like, I want to return a file and the last access time for that file. For example, that could be like a time and the file handle, or something like that. How these actually work in C++, you can construct them manually, but there's a function called make tuple, and this just takes a list of what you want the tuple to look like. And it's pretty much that easy. The weird thing is to access them. I'll show you a better way in a bit, but you use std_get and then the integer of the index of the tuple. So like if you want to access the first value, you do 0, but you know it's 0 indexed. Like in this case, we want to get the string here, so we insert the string here, we do printf, and we get the first index, and so we get the variable. I'll show auto later, but auto makes this like way nicer because it removes the need to declare the full type, which is just nice. Optional. I feel like I've already probably told people to use optional. I remember telling someone. This is another one that I use on the daily. Basically, this is a struct that either holds an object or it holds nothing. So basically, this is used whenever you want to temporarily have nothing that's going to be filled with something later, or for example, return from a function that may return something or not. So normally, like in C, what you would do is you return something on the heap and pass a null pointer or a pointer to the value. In this case, you would return std null opt. So std null opt is just a default constructed option that's just, there's nothing. It's marked as nothing. Otherwise, because C++ has a bunch of implicit stuff, if you assign anything to a std optional with the value it's templated to, it will just be that value. And so how you actually access things is with an if test. So if you do if the optional, that if statement will only be true if there's something in that object. So this is the equivalent of doing like if the pointer is not null, essentially. And then to actually get it, just like a pointer, you dereference it. So it's just like using a null pointer, basically. They designed it to like replace that. But again, you would use this everywhere. I just used it today in ROS because I had like, I'm going to get the configuration for a camera from a topic, but when I'm constructing my class, I won't have that yet. So instead of just default constructing a zeroed out struct, which could be a valid configuration, I mark it as std optional of that like configuration, and so I can check if we've received that configuration yet by just doing if we have a value, and then when we have a value, we just assign it, and then everything works as normal without having a separate like flag, basically. But again, very useful. This is probably the best part of C++ 17. Std algorithm. So this is a different header than, this is like out of collections, this is into algorithms. The standard library has so many algorithms, it's ridiculous. There's a like 40-minute talk, 105 algorithms. There's a talk at the bottom that basically goes over how to use these. Another one I would super recommend watching, it's very entertaining. Basically, these are things like quicksort. You have search functions. You have, you want to create a heap, you can create a heap. You want a binary search, you can binary search. You want to calculate the hypotenuse of a triangle, that is a function. I'm not joking. Or even like really advanced things like if you use Python, reduce and accumulate from that language are here. So like iterator operations. That's not even scratching the surface. It's insane how much is here. I'm not going to go over this too much just because that would take all day. But I would highly recommend looking at the docs to see if they have things like hypotenuse, if they have that, or like clamp is a huge one. It clamps to a minimum maximum value, or min and max, and like all these super basic algorithms are like find the first of n is one of them, where it just takes a lambda and it just finds the first of n. These are going to always be more efficient than what you're going to do. These are always going to be more tests than what you're going to do. So just try, bias towards using them is my suggestion. And I don't want to watch the video. Go away. There it is. For them, there's this beautiful website. You will love this website. This is cppreference.com. This, by the way, is the entire standard library. This website's awesome. It's the de facto main docs of C++. So, for example, let's say like, oh, I want to find like the like hypotenuse. I forget how to spell hypotenuse. Just search it there, find the page, and like, oh, there it is. And these go over every overload. They have like thorough docs of like what the function does algorithmically, parameters, how it returns, and then some example code. So this is just a great site in general for anything C++. This is like, it's good. Use it. I have this bookmarked for a reason. It is incredibly useful for class and the club. Ooh, why is it not full screen? Please full screen. All right. So where am I in the PowerPoint? All right, we got time. Okay. So I want to get through at least a few of these features here. And these are what I mentioned before of like, you probably don't know these yet. First off, all right, so here's actually, this is water drink time. So this is where the CS program here really leaves off. And I find it annoying because RAII is extremely important for C++. It's like if you ever watch like a conference talk on this, they all refer to this constantly. The docs refer to it constantly, but no one teaches it. So this is very much a C++ like design idea. Basically, it is resource acquisition is initialization, which it's more resource destruction is destructor is more accurate. Essentially, all this is doing is by exploiting the fact that destructors will always run when a class goes out of scope, we can bind the freeing of resources to that destructor to guarantee we never forget to free. That's the whole concept. And so the resource acquisition is initialization, is to do that pattern to say, let's say I want to have a file handle to something. You would get that file in the constructor to guarantee you own that file. And then in the destructor, you would release that file handle. So the idea there being you can never forget to close that file. And that's like the motivation. This applies to a ton of things. This could be a mutex, this could be a file, this could be memory, this could be a peripheral on a microcontroller. It's a very profound kind of concept when you really work with it. And this is how things like std vector or the standard library string, under the hood they're on the heap. That's the only reason you don't have to manually free them, is because in their destructor they free the memory for you. So like this is really like the big design feature of C++, and especially in something like ROS, like everything is automatically freed, and so you almost can pretend like it's a garbage collected language like Java, which is really cool. So I'll get into more of this here, but I believe in a few slides is smart pointers, which we'll do this more. I'm gonna skip this. Before that, there's just two random features I wanted to throw in, and I couldn't figure out where to put them. Structured binding. This is just cool. So you see in the bottom right, basically what it does is it takes literally any struct, and it just takes its fields and just puts them into variables. So like, for example, in the tuple we had earlier, we have like tuple of 3 things. You just do auto, and then an array with your 3 variable names. This isn't actually an array, it's just the syntax. And then that will unpack these 3 variables into these 3 variables. I only mention it because with tuples especially, this is like basically Python, which I think is pretty cool. The cool thing is that it works with arbitrary objects. It's like if you have an x, y, z vector, you don't have to have the vector and assign it to 3 variables. You can just do it in one line. It's just a nice quality of life. All right, the stuff I really wanted to get to. So smart pointers are easily the most important thing to learn in modern C++. It is basically every major framework uses them. They're very cool. They're the reason C++ is like, a language still worth learning, in my opinion. So basically, this is the application of RAI, I can't say that fast, RAII to memory. So I mentioned before how like, oh, memory is a resource that you allocate and you free. Smart pointers are just a standardized form of that. So basically, there are 3 like main approaches to this. There's unique pointer, there's shared pointer, and there's weak pointer. Essentially, these are all different models of how do we want to free this memory. So in all cases, we allocate something on the heap, and then on some condition, we deallocate it. So a unique pointer is just like a normal pointer. It's basically this pointer points to something in the heap, and whenever whenever this unique pointer is out of scope, we call dealloc or delete in C++, to free that memory. The big thing is that just through move semantics that I'm still not teaching in this, it is a compile time error to copy this. You cannot copy it. The idea being you want to avoid a double free. Because if you think in a normal pointer, if you have 2 copies of a pointer and you delete on both, that's a segfault. In this case, it is a compile time error to do that. You literally cannot. And that's where the safety comes in. Then, this is pretty limiting because obviously generally you want to have like multiple references to one value in the heap. That's pretty normal. That is where shared pointer comes in. So shared pointer is almost identically to like the Swift and I believe Python memory models, which is kind of funny. So it's a reference count. So basically, a shared pointer has 2 things: a control block that counts the number of shared pointers pointing to the same object, and a reference to that object in the heap. And so essentially, whenever you copy a shared pointer, it increases that reference count by 1, gives you that shared pointer object that you can dereference to get to that value. And then when they go out of scope, it decreases that reference value. The idea being basically you can have like one shared pointer, create 18 copies. It records that there's 18 of those. And then some go out of scope, then it records that there's 14. And it only ever frees the memory when all of them are gone. So it's the same principle as garbage collection, but it's in C++. And so things like ROS use these absolutely everywhere. Like everything in ROS is a shared pointer because you can basically treat it like it's garbage collected. Like you can just throw around these objects wherever, and then it's the kind of the compiler's problem. Weak pointer, I won't get into much, but basically it's a shared pointer, but it doesn't decrease the reference count. So if you create a cycle, it won't leak memory. Because if 2 shared pointers point to each other, then it creates an infinite cycle and they'll just leak memory, which is kind of funny. So example of what I was mentioning earlier, of like C-style stuff. So you like allocate an int on the heap. What? Oh, yeah, here. Allocate the, see, I didn't even notice it. Allocate an int on the heap. goes out of scope. We never call delete. We just leak that into memory. And as another example, we put an int on the heap. We then delete it. We then delete it a second time. My program is now crashed. These are like that. This is what it's trying to avoid. So more, I guess, does anyone have questions on the concept before I briefly go over how you use them? Maybe? You seem conflicted.
Just want to see how it's used first.
Okay, yeah. So unique pointer is single ownership. So this is, I mean, it's pretty simple. It just wraps a single pointer, frees it when it goes out of scope. It's literally that simple. So in terms of how you would actually use it down here, you have the type is std unique pointer templated to the inner value, and you construct it with this function called std make unique. So what this does, it uses some cool more C++ features I'm not mentioning here to call the constructor through the method arguments. It's really wild. So like in this case, what you pass into here is passed into the constructor of the thing on the heap. So like in this case, it's an int, so we're just default constructing it into 0. But this is what actually constructs it and puts it on the heap. And then after here, you dereference it like a normal pointer, and of course it just frees automatically. It's really that simple. The thing to remember is that if you're storing it in like a class field, or like a ROS node, it will be the type std unique pointer. Like you can't treat it like a normal pointer. That just it's not the same type. So I've gone over most of this. Again, the big thing to remember is that you can only ever have one reference to this. So this is really only useful if like you have a network buffer inside a class, for example, and you just want it to automatically free. That's really the only use case. Shared pointer is much more common because, of course, that use case is limiting. So I have a little like demo of a much more complicated example down here, but I think it's worth making it look a little more like you'd see in the real world. So basically, we have an image struct here, a window, and a function called show. The idea being like this is like a GUI framework, and you can show an image in a window. So of course you don't want to copy that entire like 5 megabyte image every single time you do it, so you pass a pointer. In this case, we want to make sure that like, I don't know, maybe the window has it on for longer, maybe the main function doesn't want the image anymore. We just make it a shared pointer to let the compiler kind of handle, you know, when it gets freed. So in this case, we would take a shared pointer of that image to the show function, and then if we, when we get the image in the first place, we would allocate it on the heap. So this is where it starts. So it's std make shared, just like make unique, creates a shared pointer towards an image on the heap. We return that from our function here. We call that over here in main. So now we have the single image on the heap. Then we call the window show function and just pass that shared pointer. Now the cool thing is that this here is, because of the way copies work in C++, as we mentioned earlier, this will automatically copy the shared pointer. And so now over here in this function, while we're still pointing to the same image, it is 2 separate pointers. And inside the actual shared pointer, it says there's 2 references. And so let's say this keeps running and somehow this image goes out of scope. Even though this image is gone, if you just use like a regular reference, this would be referencing deallocated memory. That would be a seg fault. In this case, even though this image is gone, because this is a shared pointer, it keeps it alive for this one. And then whenever this image is done being used in the window, then it'll finally deallocate it. And so that's like more of a, I guess, useful look at how it's used automatically. Okay. Yeah, that's because it's called in its destructor. So again, the big thing that you have to think about here is you cannot create cycles, because if you create a cycle, then they both keep themselves alive for forever. So for example, you cannot make a linked list out of this. You cannot make a graph out of this. Pretty much any graph you can't represent just with shared pointers, and that's where things fall apart extremely quickly, and you almost have to use raw pointers. Or the other option, weak pointers. Literally, weak pointers exist purely to solve the exact problem I just mentioned of like you want a linked list. They are literally just a shared pointer, but they don't keep it alive, which sounds terrible because that's just a regular pointer. It's literally just a regular pointer at this point because it can point to null. So how you actually use it, you can see over here, you have a shared pointer. You then construct a weak pointer. It has a constructor that takes a shared pointer, so equals does the same. That creates a weak pointer towards that shared pointer. And then there's this function called lock. And what lock does is if, actually I don't know what it returns. I think it returns std optional. I could be wrong though. But basically, lock returns an object that's false if the shared pointer has been deallocated, and true if it's still there. So for example, to get that image, if lock returns true or a truthy value, that will be the image, and we can use it. That's the same as getting it from the shared pointer. But if it's been deallocated, normally if you like just raw dereference that in C, again, you would segfault. In this case, we can manually check to see if something's allocated or deallocated to avoid, segfaulting. Because in C, you can check for null pointer, but you can't really check for this memory. We no longer own this memory, and the OS will scream at us if we access it, right? There's literally no way to do that. So this is giving us a method to do that. Again, you probably won't touch this. It's just be aware that, like, especially in like CIS 350, when you start making graphs, if you want to make a graphs that free themselves, which is super sick, you have to use weak pointers, and Ross touches them occasionally, just to avoid cycles and leaking memory. I think, how much do we have? I'm just gonna finish this because I don't want to leave 3 slides, but I'll try and be pretty quick here. So Auto, I've been using Auto a ton. Auto it's exactly the same as var in C#, JavaScript, or not JavaScript, C# and Java. Basically, you put it wherever you would put a variable, and that variable can be automatically deciphered, or that variable's type can be automatically deciphered by the compiler. It's like, for example, you can't put Auto in a like function signature because like it would have no idea what you want that type to be. So it's not dynamic typing. This isn't Python. But for example, here, you have auto I equals 1 and int j equals 1 they're literally the same. See, it just automatically determines the type. It's really as simple as that, honestly. It's not like you're removing the types. Like, it's still typed to this type. Like, again, we're not JavaScript, but it just removes extra typing. So like the shared pointers especially, like, look how long this line is. It's stupid. You can just put auto on the left-hand side because it knows what's returned from this function. And then it's just clean, and it's pretty, and it's nice. In my opinion, and this is kind of a mantra in the C++ community, almost always auto. So basically, default to auto except for integers and floats. And the reason for that is that generally I want like a 16-bit integer. If you use auto, it will default to not that. So that's like the only time where like explicitly making the type matters. Or if you ever wanted to make it abundantly clear that like, this type is very specific, there's semantics to it being this type. Otherwise, just use auto everywhere. That's what I do. It makes your code so much cleaner. And the cool thing is if you change the type of a return type of a function, everywhere that uses that variable is already updated because they're all using auto, and the type is implicit. So you don't have to go and update the type, in 50 header files or whatever. Yeah, just nice feature. This has been around since C++ 11. So you can use it wherever. Basically zero cost. Literally zero cost. Last big thing, lambdas. So lambdas, has anyone here used lambdas? Oh, you've used lambda. Oh, Java. I'm like, yeah, I'm surprised you've used lambda and you haven't taken 200. You've used them. Okay. So.
I've used it, but not in code.
Wait, what do you use? What are you talking about?
Never mind.
What are you talking about?
No, I'm talking about discrete mathematics too.
Oh.
Yeah.
Oh, lambda calculus?
Lambda. Is that what this is? Is a lambda?
Lambda.
Lambda. I think it's different then.
Okay, whatever. So in this case, lambdas just mean a function that can be treated as a variable, which itself is actually kind of a profound concept. But basically, you may have heard them called higher order functions, closures, anonymous functions. Basically, they're just an inline defined function. So like in the C++, syntax is a bit weird. It's a reference list, the function args, a return type, and the function body. So I have an example here. So like, for example, this function is a function that closes over I. I'll talk about that in the next slide. It has an argument of j, and it returns I plus j with an implicit return type. We can then assign that to a variable. So we can assign a function to a variable, which is crazy. In this case, you literally have to use auto. This is the reason. This is the reason auto was actually introduced, is because this lambda doesn't have a type. In some languages, it does have a type, but in C++, it doesn't have a type. So, no, the lambda is... The C++ doesn't have a notion of like function types. Like, you can't say this variable is a function that returns int and takes an int. So basically, this is an untyped variable as far as you're concerned. And so to use it, you just call it like it's a function, and then it works. So you can see on the right how you actually use these. You have to use templates. You literally cannot use a normal function because, again, you don't know its type. So you have to template over it. But the nice thing is because it's duck typed, you just make a template and then just pass it. And then so long as that lambda can be called with what you call it within the function, that template will compile. And when you're passing that lambda, actually, I don't know if you have to pass lambdas by reference or value. I actually don't know. Do you know? No. I actually don't know. That's an interesting question. I'm actually not sure. You could probably look that up. But basically, like we have our lambda here. We have a function that takes a lambda. So we can pass that lambda as a variable and have that done in the function. And so the reason you would do this is, for example, in like a ROS callback, like a ROS subscriber callback is a perfect use case for this. You can pass a lambda to the callback, and whenever that subscriber gets called, your user function is called. So essentially the motivation of having these lambdas is you can pass not just data to a function, but an action to a function. And that function can be like a standard template that works across all of those various lambdas. And so probably the most useful thing to use that for is Clojure. Clojure is it's a simple concept, but it sounds fancy. Basically, the idea is that think of like when we're declaring this lambda here, we can access variables in the outer scope because you can always do that. I mean, that's just normal. But if you reference, for example, I here, I in the function, this I will always be this I. But the thing is that we can pass our lambda wherever we want because it's a variable. So like, for example, we pass this this lambda into this add function. Now, I'm stupid and made a second I variable, but if pretend this I is like j or something, we have no way of accessing this int from add normally, because of course they're two completely different function scopes, so why would you have access to it? But because the lambda here referenced I, that is closed over I is like the fancy terminology for it, when you call the lambda in a different function, it will still have a reference to this int from the other function. So it's kind of weird to think about, but you can do some really, really powerful things with this. Because you can pass, for example, let's say, I'm trying to think of a good example now. But like basically whenever you have a callback to something, like I'm trying to think of a good use of this. It's one of those things that you honestly just kind of intuitively use. But basically, you can use this as a way to essentially pass extra parameters into a function. So for example, let's say you want to have access to like an image inside of a random function. You pass, and it doesn't take an image. Inside your lambda, you capture or you close over that image. And then because your Clojure can still, or your lambda can still access that image, you've in effect passed the image to the function. And that's really its big use case. Again, you don't really have to think too hard about this because it works like normal scoping, but just keep in mind that this is how you can pass variables you wouldn't normally have access to and create more generic functions. The important part, because this is C++ and we aren't garbage collected, and like Java, you just do this and it's like, the garbage collectors, it's their problem. In this case, we have to deal with the fact that like, just because we can auto-magically access I here doesn't mean like I exists and we won't segfault. So in the first part of the lambda, this index bracket, which is like kind of the weird syntax here, you can pass three things: an equal sign, an ampersand, or a name. If you do an equal sign, it will essentially make all of these pass by value, so it'll copy all of the variables. You don't have to worry about references in this case because, of course, they're all just copied. This is the safe choice because you just forget about memory, but of course it costs action to copy. If you do an ampersand, it passes everything by reference. And in this case, you do have to be aware of how this works because, again, if that it's an int, but let's say that was like a pointer or something. If that goes out of scope and you've saved this lambda in like a class somewhere else that outlives this function, it will segfault when you access that I, because that I no longer exists. This is just something to be aware of. Again, this is like where shared pointers come in useful, because let's say that I was a shared pointer. You would copy that shared pointer. If you do the equal sign, so if you have all them copy, it would copy that shared pointer, and then it would ensure that you would never have a memory access issue. and then that I would be as valid as long as either test scope is in scope, or as long as that lambda is alive. So again, just another reason for shared pointers. And then the final one, name, just means it will only let you capture the variables that you have passed that name for. So this is just for errors. Like if you have like, the entire alphabet as single letter variables and you create another A inside your lambda, it's then a compile time error if you didn't explicitly say, I want to pass an A. So it's just for like, it lets you avoid accidentally passing in things you didn't expect. As well, in C++ 17, and thus in ROS, if you want to capture the this pointer, so if you want to call a method in a lambda, you have to explicitly close this. And then you do this dot whatever method. And this is just because it's extremely error prone if you just call a method without this in the lambda, and then you pass that lambda outside the class, then everything blows up immediately, and it's just chaos. But in ROS, you use this a ton, because every time you do a subscriber callback, you have to pass the this pointer. So just a reason I mentioned that. Okay, I've already explained that. All right. You know what? I'll leave these last three for homework, because frankly, iterators don't matter as much, and I've already gone over. I guess TLDR of iterators is they suck, and they're very terribly designed. So the real answer is this: call.begin and call.end, and then that's your iterator. We're done with iterators. So this PowerPoint is like almost a living document in that I keep finding more things I want to put in it. Like we didn't even touch on concurrency or like calendars and time, and like there's so many weird things. Or all of stood bind, like there's just so much. So I'd highly recommend checking out that C++ reference site. If you just Google C++ reference, it comes up as the first thing, both in class or just, I don't know if it's just me, I just read it for fun, just to find like weird niche things that were created in the 90s that I've never heard of. There's a bit vector that can do like linear algebra operations. Like it's so weird, but it was like just this weird failed experiment from the 90s. Like there's a bunch of stuff like that in there, and it's just fun to read. Or like if you learn concurrency, learning the concurrency is super useful. It's just fun to peruse because there's a lot of stuff that's very useful. But C++ is a bit of an info dump language, as you probably noticed from this PowerPoint. So having a reference to look at is extremely useful, and it's extremely good. So anyways, I highly recommend using it. Very useful. And yeah, next week, I really want to do our big autonomy class. Basically, it's my summary of mobile robotics in an hour, which is an insane ask. It'll probably go over an hour. But especially for, all of you, any of you that are undergrads, so everyone but this man, unless you take the mobile robotics course, you aren't going to learn this. And especially, just no matter what you do in the club, our club is mobile robotics. Like, that's our club. So this is like a very useful lesson to be due. Please show up. That would be nice. But even just for you, it's going to be a lot, but I hope it's going to be useful. I was going to do it today, but then some people couldn't show up, so I wanted to push it back a week. Yeah, anyways, look forward to that. I'm excited. I love teaching it, and it should make both TinyCard and Phoenix way more clear, because, it's basically to what I understand of the field. So if you can understand that, you're pretty much, you know as much as I do in terms of the high level, which is going to be fun. So anyways, look forward to that, and yeah.